talk with this pair is Craig Boutilier, who will tell us about reinforcement learning for recommender systems.
Great. Well, thanks very much. Thanks for the invitation. I apologize for not being able to be here for the whole 4 days because it looks like a really interesting workshop. Not too much travel, but definitely learned a little bit about the state of the art in RL today. So this has been great. What I want to talk about is some work that we've been doing at Google with a number of collaborators. As I go through a couple of pieces of work, I'll mention the collaborators. A couple are here, Yishai, Dale, here in the room today. So the work that I've been focused on over the last little while, and folks on my team and some of our collaborators at Google and beyond, has really been on recommender systems and the application of reinforcement learning to recommender systems. And really one of the things that motivates me and motivates a lot of the work that my team is doing is the need that we feel to make our recommender systems more user-centric, right? Now that's a bit of a buzzword, but what I mean is simply just a really simple slogan. We want to build recommenders that really understand a user's genuine needs, goals, tasks, preferences, and can do a good job of meeting those needs, subject to those preferences, understanding their tasks, and interacts with the user in a very natural, unobtrusive, and transparent fashion, right? Now, what does that mean? That's a mouthful. I could probably spend about 40 minutes just trying to unpack that. But I'll just boil it down into kind of 3 main bullets that really drive my thinking about recommender systems. The first is that we think we need our recommender systems to do a better job of understanding user latent state. We've heard a little bit about hidden state here today, but this is something I don't think gets enough attention within the RL community these days. And for users, when we're interacting with users, latent state is super critical. When we're talking about latent state, we can mean, how satisfied is the user with their product? What are their current preferences? What are their needs? What are their interests? What activities are they engaged in? Many of these things are going to be transient. Some are going to be persistent and extend over long periods of time. And we really can't act well on behalf of a user without understanding that. Okay. The second point here, when we talk about natural interaction with users, we're going to have to take efforts to estimate, react to, and influence, and in particular, elicit that latent state from users. We're going to have to get crude signals about what it is that they want us to accomplish, or recommenders to accomplish for them. If we're going to do that, we're going to have to interact with our users in a much less brain-dead fashion than most recommenders currently do. We're going to have to engage in true multi-turn, multimodal interaction, and generally we're going to have to engage in dialogue and conversation with our users to be able to act on their behalf. Okay? And finally, we want to do all of this so that we can really act in the user's best interest, right? That means not only understanding user preferences, but when we observe their behavior, when we try to make inferences about what that reveals about their preferences, we've got to be cognizant of the fact that how people act can sometimes not give a true representation of what it is that they're trying to accomplish. Okay, so these are a lot of things that motivate our work. And it should be pretty clear, I think, to everybody here that reinforcement learning is going to play a central role in all of this, right? If you look at the first 2 bullet points, for example, that requires thinking about a sequential interaction with users and planning how you gather information, how you talk to them, and how you interpret their responses. Okay? Now, I'm going to give, this is going to be a very high-level, mostly non-technical talk. Feel free to interrupt if you've got any questions, but I'll follow the gradient that Dale said, not being theoretical. I don't know why that's not theoretical, but I'll follow that gradient up to its limit. So now the real question is, if RL is going to have to play a central role in all of this, but the real question is, why haven't we seen RL applied successfully? Maybe in little bits and pieces, a little bit at Microsoft, a little bit at Facebook. We've had a few minor successes, I would say. I would say at Google. But despite all the great successes RL has had in game playing, simulated environments, in robotics to some extent, even in physical control of things like data center cooling, that's some work we've been doing at Google. Somewhat surprisingly, we've seen much less success in the application of RL in user-facing applications. We're talking about, say, ad serving, or in particular, what I'm going to focus on, it's recommender systems, right? And why is that? Okay? What I'd like to challenge people to think about is, what is it about these types of problems, which are really important from a practical perspective, that the RL research community is missing, right? I don't have solutions to all of these. I'll just pose a couple of these and talk about some of the starting points and some of the work that we've been doing along these lines. But for me, you know, we want to chart like a 5, 10, 20-year path to really bring RL put it really in front of users on a day-to-day basis. So what are some of the challenges when we think about applying reinforcement learning in user-facing systems, and in particular in recommender systems, right? We often hear about scale. I guess we haven't talked too much about scale at this workshop, but you know, we think about, oh, Go is such a complex game. The number of actions, the number of states. When we think about recommender systems, usually we're talking about systems that are interacting with millions or billions of users. Now, interestingly, each one of those users, at least at one level of abstraction, is almost like an independent environment, right? Each user is their own MDP. The action I take for one user doesn't influence another user until we start thinking about ecosystem and game theoretic effects, but I won't talk about that here today. But you know, we may have billions of users. The number of actions that we have is often in the order of many millions, if not billions. If you think about, say, recommending videos on YouTube, each possible video in the corpus is an action that I could take in a recommender system. Okay? But it's worse than that, because you don't go to YouTube or go to an e-commerce site and get one item recommended. It's usually packaged together in a slate. You get a bunch of things, right? So now we've got this combinatorial blow-up in the action space that we have to deal with from an RL perspective. It's really critical from a practical point of view. Second problem is the idiosyncratic nature of our action space, right? When we think about a slate of items that we're putting in front of you, it often doesn't have a fixed size if users may be scrolling through their mobile app to find a product. How many items they're presented with is often dynamically created. And often the set of items that are recommendable is actually stochastic. There's some exogenous stochastic process that's generating, hey, here are the things that you could recommend right now. And surprisingly, from an RL perspective, we really don't think about problems like that. Finally, and I think the most important one, is dealing with user latent state. As I already mentioned, we care about a user's preferences, their activities, who they're with, their personality, their preferred modes of interaction, and so on and so forth. And all of those things are really critical to deciding whether or not this is a good or bad recommendation, if this is the right time to make a recommendation, what have you, okay? But because of this, we've got a tremendous degree of unobservability. When we interact with users from a POM-DP perspective, the signal that we're getting about that underlying latent state is really, really small. Chuck?
Can you take kind of a statistical approach, rather than trying to understand the hidden variables and the hidden states, just say it's a black box, and there's so many of them that I can statistically estimate and be successful on a large majority?
I mean, so we really wanted to be in my goal is to put what I would call true decision support tools in the hands of every user, right? And everybody in this room has very different preferences. There's a lot of commonality, and we'll absolutely want to generalize across users. All our models do, but I really want to understand your preferences. And from my perspective, it really requires that I'm going to have a conversation with you. Like a person that was interacting with you and making recommendations, you'd have no trouble saying, hey, here's a little bit about my preferences and the trade-offs that I'm prepared to make. Our current recommenders don't do that, right? That's the only point that I want to make. Now, does it mean we have to explicitly represent that latent state? We could, I'm perfectly fine if we just take all of that data, a user's entire interaction history, run our favorite RNN technology and say, hey, I've uncovered a belief state representation. The problem is our technologies, they're nowhere near being able to do that right now. Right? I'm okay with that though. If that's the way we do it, that's fine, right? But we can't do it that way. Okay, so the key thing I want to point out that there's a huge degree of unobservability and a huge degree of stochasticity, right? So when I recommend a video on YouTube and the user then just shuts down the app, was it because they didn't like the video? Or did somebody ring the doorbell? Or did their kids say, hey, I need some help with my homework, right? We don't know. Highly, there's so many exogenous factors, highly stochastic. So it all adds up to a very high, a POMDP environment, a partially observable environment, which we have to do RL, that has a really low signal to noise ratio, right? Really, really challenging. Okay? And I'll explain why we think it's important to address this in a few minutes. And of course, there's all kinds of other stuff. I think, Dale, you mentioned at the top of your talk that there are multi-agent interactions. We're very interested in things like fairness, ecosystem dynamics, incentive properties, some of the game theoretic and multi-agent aspects as well, but I won't talk about that here. Oops. Page unresponsive. Wait. Oh, I waited long enough. Great. All right. So what I'm going to talk about today, I'm just going to pick 3 topics from here on some work that we've done, highlighted in yellow. And the degree of yellow tells you roughly how much time I'm going to spend on each. So I'm just going to give a very high-level overview of this one idea of stochastic action sets, work that Dale and Yishai were involved in. Talk very briefly about some more recent work on dealing with user learning and how we handle the low signal-to-noise ratio. This is very preliminary, very far from practice. This is actually we do this in practice. And then I'll talk about some work in a little more detail at the end on how we're handling the Slate recommendation problem from an RL perspective. And this is something that we've also put into practice. Okay. So let's start just really quickly with this first problem, that of stochastic action sets. Okay. So it turns out that in a lot of user-facing systems, whether we're talking about ad serving, recommender systems, that the set of actions that you're able to take at any particular state is governed by some exogenous stochastic process that's out of your control, at least out of the control of the RL algorithm. For instance, in ad auctions, because of things like budget throttling, campaign eligibility, in recommender systems, because of various candidate generation and eligibility criterion, what can happen is you can be facing a user, you're given a set of ads or recommendable items that you can put in front of the user, you go ahead and you do it, user responds in a certain way, maybe they didn't like that ad, end up in a new state in your MDP, you're given another set of ads that you can show. You show one, user responds in a certain way. You end up back in state 1 or something equivalent to state 1, and you get a completely different set of actions. Right? This sounds, I think Dale, you agreed when we first talked about it, this should be a problem that the OR community solved, decades ago. Right? Surprisingly, though, Surprisingly, though, the foundations for this type of model just didn't exist, right? But this is a problem that we have to face in practice in recommender systems and in ad systems, right? The problem is it doesn't naturally you can't naturally formulate it as an MDP, so it's very hard to do RL, right? So we thought about how would you go about solving a problem like this? Darn it, Dale.
You can
What's that?
You can exit that page. It's not about your current page.
What's that?
It's not about your current page. You can exit that page.
Yeah, I think it's a
What?
Gmail window.
It's about your Gmail.
Oh, I didn't notice that. Okay, let me just close a bunch of stuff here.
Yeah, that should work.
There we go. That was weird. Okay. I wasn't actually reading the message, though. Let's go back. Okay. So how would we go about formulating a problem like this as an MDP? And again, I'm not going to get into a lot of technical detail, but roughly speaking, there are 2 ways to do it. One is, so the process that we're engaged in, we show up in a state and nature is going to say, here are the actions that you're allowed to play right now, okay? So you're at a state S, nature says, here's a subset of the feasible actions that you're allowed to play, okay? Right? One way to think of this as an MDP is just to embed the available action set within the state space itself, right? And then if we know if we know something about the action generation distribution or that process, then we can easily build a transition model within this embedded state space, okay? The problem with this is it blows up the state space exponentially because we have to have a copy of every state for every possible subset of actions. The second way to do it is not to blow up the state space, but simply say our actions at a given state are the set of mappings that take the available set that's revealed to us and tells us what action to play from that particular available set, okay? And again, if we know what the action generating distribution is, very easy to construct a model. Now we didn't blow up the state space, but we have this factorial blow up in the action space, right? But both of these things are now nice MDPs, right? But they don't look very tractable. Fortunately, despite this blow up, we can show that the optimal policies and the optimal value functions, of course, actually are provably compact. They have this really nice representation. Yep.
So just to make sure the process that's governing which actions are feasible is not influenced by the policy, right? It's exogenous.
Yes, exactly. Yeah, there's some exogenous process that we don't have control over. Exactly right. Okay, and that's often the case in, say, an ad serving system, right? So it.
What's the S state mean here? So
What's that?
What's the S means in previous slides?
S?
Yeah. What's the state here? So what's state here in recommendation?
Oh, in a recommender system, I'll get into that in a little bit more detail, but think of the state as some user features, demographics, something about their context, could be the location, time of day, something about their historical interaction, anything that we would feed into a predictive model to predict their behavior. Right? So that'll be the state. Okay. Okay. So it turns out that optimal policies, in particular, always have this nice decision list structure. In particular, we can say at state S1, action K1 should be ordered before K2, ordered before K3, and so on and so forth. And we can do this for every state. We know an optimal policy, that there always exists an optimal policy with that structure, right? So for example, if these two actions are revealed to me as available at state S, then I would play action K2 because it's the first one in the available set that shows up in the ordering. Okay? The nice thing about this is you can take advantage of this structure to develop nice polytime algorithms. In particular, we've developed value iteration, policy iteration, linear programming method to solve these problems when the model is given to you. Most important from a practical perspective, because this is a situation that we face in ad serving, this allows you to decompose something like Q-learning from a practical perspective. I don't have to learn a Q function over this expanded state space. I can learn a Q function that's a function of the state and the individual items, and then choose when an available set is revealed to me, I just have to choose the available action that has the maximal Q value. You can prove that is exactly the right thing to do. Just recently, just this summer, around ICML time, Georgios Theokaros, Philip Thomas, and a couple of others actually have started to develop policy gradient methods for these types of models as well. Okay. All right. So let me move on. Talk about I think is maybe a slightly more interesting problem, one that's completely unresolved, and that's some techniques that we've been starting to look at for dealing with POMD, partially observable environments that have really low signal-to-noise ratio. Okay. And the thing that motivated us to think about this problem is a phenomenon that we've observed in recommender systems and in ad-serving systems. That's a phenomenon of user learning, that users will learn to adapt to a change in your recommendation policy, but over a really long, slow horizon, right? So this is a plot from some Google folks. Let me not talk about this. This is in an ad-serving context, but here's some work that folks in Google Research and YouTube did just a couple of years ago, where they changed the YouTube serving policy on the home page to show more or less diverse recommendations within that slate. Okay. And what we see here with the blue line here, what we're seeing is the percentage increase in the number of homepage visits from the users that are consistently shown given this more diverse treatment. And in green, what you're seeing is users that are given this diverse treatment just for one day, so there's no cumulative effect, right? And then another group of users on the next day and so on. Now what you see is that the change in the number of homepage visits, in the early stages, there's no difference, right? So we're having almost no impact on the user. But then over this very long horizon, and I'll point to the scale here, this is almost a 4-month experiment, okay? There's this slow but consistent and persistent effect that we're having on the user, right? Now, we believe there are also some exploration effects that are going on implicitly, but really the users are learning to adapt to this change, right? The surveys confirm this, that, hey, users are actually a little more satisfied with the recommendations that they're getting. But how does it manifest itself in their behavior in terms of, say, increased number of homepage visits to YouTube? It takes weeks and months to actually start to show up and actually converge, right? This is going to be problematic from an RL perspective. If we want to say, hey, if we showed more diverse recommendations, what's it going to do to the user if we do it again and do it again and do it again? We're talking about events with horizons that are on the order of tens to hundreds of thousands of events, right? And from a practical perspective, we can't really handle that, okay? In particular, what's going on here is these problems have what I call a really low signal-to-noise ratio. Yeah.
Sorry, stupid question. I'm not sure I got your graph. So the first one is the same user where you're showing them more diverse.
That's right.
Recommendations.
Consistently, right? So if you're part of that group, every time you come to YouTube, you're getting more diverse recommendations. Okay. Yep.
And the green one is
The green line. So we don't want to just compare it. We don't want to just compare it to kind of what is the current policy. What we're going to do is say we're going to take me. Today we're going to expose you to more diverse recommendations, and then we throw you away. I mean, you just go back and you don't do it. And then tomorrow I'm going to take somebody else. Tomorrow I'm going to take somebody else because we're trying to see, is there a cumulative effect on the user versus just kind of a one-shot thing. Yeah.
okay.
Is it cumulative diversity? Is the diversity being cumulated across different days? So
No, there's a diversity within that particular slate of recommendations, right? So it's an immediate change to the policy. Like, here's my state, what action do I take? What slate do I put in
It
front
seems
of
that
me?
there is a leakage of information because the green thing is not, otherwise you don't have to do the green, you just do the blue at the first few days and the green should be the same. But the green is like increasing variance.
The green, I'm not sure how you mean.
Seems to be increasing its variance over time.
No, I don't think that's true, right? I mean, these are highly stochastic process. I won't say how many users, it's a lot, but user behavior is highly stochastic in something like YouTube. So I actually don't think empirically this variance is actually increasing yet. I don't have the stats to back it up. I don't think that's the case. Okay. All right. So what's going on here, right? Problems like this, they have a really low signal-to-noise ratio. So if we think about, let's suppose it's user satisfaction that's driving this increased engagement, the increased return to the YouTube homepage, right? First of all, it's very clear, I mean, as you're talking about the variance, this in itself has a very noisy impact on user engagement, right? It's just one of other much more dominant factors that will dictate how often a user uses YouTube, right? But this latent state, the satisfaction, it moves very slowly, right? But very persistently. So it really has this significant cumulative effect on user behavior, which we would like to capture from an RL perspective. Okay? But it's going to be really problematic, and in particular, without getting into a lot of technical detail, I think somebody was talking about advantages earlier today. What happens from a formal perspective is that the advantages. Suppose if we think about, let's say satisfaction as just a one-dimensional latent state. Okay? What we see here, this is just a synthetic demonstration of this point, that the difference in Q values between action one, let's say showing a diverse slate versus showing a non-diverse slate, the differences in these advantages is very, very small, right? But because these are partially observable latent state problems, there's always going to be state estimation error, okay? So if you actually, say, run a Q-learning algorithm, even where you get to observe this latent state, so you don't have to estimate it, but we just perturb it with a little bit of noise, what you see is that the best action, the red action, versus the blue action, they actually invert, right? It's really hard to estimate what the right action is, all right? So what we've been doing is developing some techniques, and these are in their nascent days right now, to amplify these advantages to make the control problem in these latent state problems, in these hidden state problems, much easier to solve. And one technique we've been looking at is temporal aggregation. So for example, if we go back here, what we see is that there's some small advantage between showing a diverse slate to keep users a little more satisfied, to get them a little more satisfied versus say a less diverse slate. Okay? But if we aggregate this and we say, hey, you know what, we're not saying what the slate is, but suppose we just had two choices of action. More diverse, less diverse, and how you implement more diverse can be dependent on a lot of contextual stuff. If we aggregate it and say, you know what, for the next k time steps, I'm going to show only more diverse slates, right? And then after that, I say I'm going to change my decision for the next k time periods. Again, I'll show another fixed action. Just hold that committed. What happens is we actually amplify those advantages, right? And in the noisy case, what happens is we actually recover the proper ordering of these actions. Okay? Now, again, I'm not going to get into technical detail. I'll be happy to talk about it offline. This turns out to be especially useful in these user-facing contexts when that latent state evolves very, very slowly, right? Because what happens, suppose that I committed to an action because it seemed like the right one, but after but maybe after 4 or 5 steps it's not right. Because the state is moving so slowly, chances are, if it's not the right action, it's going to be close to being the right action. Okay? Yeah.
So I guess while I get the intuition, what worries me about this proposal intuitively is if there are actions that can, like the amount of temporal aggregation you want to do might be very different for different actions.
Absolutely.
And one of the actions was to just like offend the user.
Yep. No, you're absolutely right? So this is a fairly simple stylized model, right? You can show under certain properties of the MDP. So this type of temporal aggregation is going to work not for this type of fixing an action. It's not going to work, hey, you don't want to fix that video for a while, right? But at the right level of abstraction, if we've got the right policy parameters, it can actually work. But there are other things that you can do as well, right? So there are actually more, that was just to illustrate the point, right? There are other types of abstraction or aggregation that you can do. You could have some switching costs. So you're not forcing me to commit to an action, but you're just going to make me pay a cost if you switch. You can do the same thing using, something like soft policy regularization at the level of, but more from the point of view of switching. So I want to keep the same action distribution and so on. I think the more interesting question, though, which is why we think this is a fundamental research problem, is that it really offers a different motivation for thinking about hierarchy and macros and options. Normally we think about options as a technique for, hey, this will help me achieve a sub-goal, hit a waypoint along the way, reduce my computational effort somehow. What we think is that if we can come up with kind of local policies whose goal is to help us identify that state, amplify that signal to noise ratio a little bit. Let's not worry about sub-goals. Just let me help me figure out where I am, right? That could be a very useful motivation. We don't know how to do that yet. We're thinking about these problems, okay? Now you can do a little bit of theoretical analysis. It shows some value, but only in synthetic experiments. This is very far from practice. But I think this is one of the most pressing problems that we face. Okay. So in the last, I think I've got it still about 15 minutes or so. I want to talk about the final piece of work, and I'll get into a little more detail on this, depending on the questions. And that's dealing with slate recommendations, right? So any recommender system that you've dealt with, you've probably never been shown a single item recommendation. It's usually some collection of items, right? Buy these books, watch these videos. Here are 3 music tracks. Which one would you like? Okay. And again, I don't think I need to motivate for this crowd why we want to optimize over the long term. Okay. I think we've done a good. I think we all understand that's what we'd like to do. From an RL perspective, if we wanted to formulate this as an MDP, to answer your question about what is the state, well, we'd think about the state again as a collection of user features, elements of their demographics, something about the user's history, how we've interacted with them in the past. We use it to make predictions about how they're likely to behave in the future, various contextual features, and so on and so forth. Our goal is to maximize some notion of engagement. We want our users to be engaged with our product. We want them to be satisfied and so on. We won't say, we do some, I'll talk about some live experience. I won't say exactly what the user engagement metric is, but we did some interesting experiments with YouTube users. And our reward is going to be, again, a function of this engagement signal. So, how many videos did they watch? Did they answer survey questions? Did they like them, et cetera? And now our actions are not going to be the individual videos, but they're going to be slates of videos, okay? And this is where the combinatorics comes in, right? If we've got n recommendable videos and we've got case slots that we can fill, we've got this combinatorial blow up in the number of slates that we can configure, okay? And this is going to be problematic for a variety of reasons. First of all, from an exploration and generalization perspective, if we just think of those slates as the items themselves that have no structure, that if we don't try to exploit some structure, we've got way too many actions that we'll be able to then we'll be able to explore, and we won't have the appropriate generalization. I mean, you could come up with the right feature representation, but we want to do something a little bit more. We're also going to have a problem from an optimization perspective, because whether we're doing a policy improvement or a Q-learning maximization, we have to find the right slate given a particular state from this huge number of possible actions. Okay? So ideally what we want to do is decompose the value of a slate into something that's a little more tractable. Okay? And you'd think, well, maybe I could just think about the value of individual items. But the problem is that items on a slate interact with one another. In other words, the presence of one item on a slate can impact the value, or I should say impact, for instance, the probability that the user will select some other items on the slate, and hence will impact the value of those other items on the slate. For example, if I get a slate of John Oliver video, here's a John Oliver video and some other political satire videos, the probability that I'll click on this video in this slate is probably pretty different than the probability of me clicking on it in a slate full of funny cat videos, and I'll let you guess which one has high probability. All right? Okay, so specifically, we want to take advantage of the fact that the value of a slate depends on the user choice model, right? What is the process by which a user will select one item from the slate of items? Okay, there are a variety of user choice models that you could imagine. Common one in stats and econometrics and the psychology of choice is just a simple loose shepherd or multinomial logic, or I think more properly a conditional logic model, which simply says, give me a slate A, this capital A here, in a particular state S. The probability that the user will select an item I from that slate is simply the exponentiated value, where this value represents some attractiveness of this item to the user, right? A very common choice model. But there are many other choice models, Placket Boost, Cascade models, and so on. There are a variety of models that you could use. The point is, when there's this interaction, generally it's going to require joint optimization of the slate. So how can we take advantage of that? So we've developed a technique, we call it Slate Q, which decomposes the value, the Q value of a slate, so this will be a Q-learning technique, the Q value of a slate into item-wise Q values. And in particular, and this assumption is valid when we make just a couple of specific assumptions about the dynamics of user choice and how it influences state evolution. Next slide will say what those two assumptions are. What we're going to do is learn, we'll call them conditional on-click item-wise Q values. So for every item that we could recommend, we're going to learn what is the value of that item, if the long-term value of the item, if the user were to click on it. Okay? And then the Q value of a slate will be derived from these item-wise Q values in a very simple tractable way. And of course, the values of the slates will also feed into the learning of the item-wise Q values, because we don't see how users interact with individual items. We see that they interact with slates in our training data. Okay, so I'm going to make two simple assumptions that are relatively innocuous and hold approximately in reality, that are going to allow this decomposition to work. Okay? The first is that when the user is presented with a slate, they're going to select only one item from that slate. Okay? That's actually the case, for instance, in YouTube. Well, now you can queue up YouTube videos, which throws a wrench into all of this. But you look at the home page, you click on a video, maybe you go back to the home page and see the same videos. Your state has changed. You've done something different. So it's a different event. So from our perspective, you only choose one item per event. Okay? So that's perfectly fine. The second assumption is that the state transitions and the rewards, the probability of going to the next state from the current state, depends only on the item that the user selected, not on the items that they didn't, right? Now, and the reward as well depends only on that item. The reward, that's okay. We're interested in how you engage with the videos that you consume. The state assumption is probably, it's only an approximation of reality. The videos that I showed you that you didn't click on can have an impact on your state, but to a kind of a first approximation, this is not an unreasonable practical assumption, okay? Well, once you do that, the details aren't super critical. The paper, you could all derive this in about 2 seconds. With that, you actually get a full decomposition of the Q function, okay? In particular, here I'm just showing the on policy. What is the value of a slate at a state given a fixed policy pi, right? You can do the same thing when you want the optimal Q function. It just decomposes into this nice expected value of these itemwise Q values. So we're going to call this thing a Q bar. It says what is the long-term value of a user consuming item I, right? Conditional on them clicking it, okay? And that thing, so that's what Q bar refers to, given a fixed policy pi, where that thing depends in the obvious way on the value of, on the standard value function, okay? Now the thing to notice here as well is that we're taking advantage of this user choice model, right? And these models are actually, we learn these things all the time from data, okay? You can think of it as a PCTR model. Here are 5 items on the slate that's capturing interactions. What is the probability user will click on this one, this one, and this one, okay? And I should mention, I think I forgot to mention it, we always assume that there's a null item on the slate. So the user can always not choose anything, right? So we don't treat that specially, we just assume that there's this special item on the slate, okay? So this is all very nice. I won't go into the details, but it now suffices to just learn these item-wise Q functions. Okay, we don't have to learn the Q function of a slate. We can compute that on the fly from the item-wise Q bar functions. Just in the interest of time, let me not go through this. But you know, the Q value update for kind of TD on policy SARSA style updates is very straightforward, and you can do the same thing if you want to do full Q learning. The only difference here is that we have to throw in this max, okay? And this is the second problem that we face, right? When we want to do this maximization, right, we actually have to find, out of all possible slates of items, we have to find the one that optimizes this expected Q value, this decomposed expected Q value, right? So now we've got a combinatorial optimization problem. We have to solve it at serving time, obviously, when we want to compute the slate, but we have to solve it at training time as well, with every SA, where A is a slate, SA, S primed R tuple, we have to solve this optimization problem to be able to do a Q backup, right? And that's potentially problematic, right? But it turns out, at least depending on the user choice model, that this actually has a nice tractable solution, okay? So if you think about this problem, it's actually very similar to a product line optimization or an assortment optimization problem where users are making choices based on characteristics of the individual items, but to a vendor, each item has some profit or revenue that it generates. And I want to put together a slate, put products on my shelf that are going to maximize the expected revenue for a certain population of users. The only difference here is what we're trying to do is maximize the future expected value of these items for the user as opposed to some notion of revenue. But otherwise, it's formally equivalent to these problems. So we can formulate it as just the typical way to formulate it is as a fractional mixed integer program. Here, this would work for, say, a conditional logit or multinomial logit model and various generalizations. Don't worry about the details. Yeah?
One simpler solution is to just sort by Q bar, sort the items by Q bar and take the top.
Next slide. Yeah, will come, right? Not optimal, unfortunately.
Yeah,
right.
But how bad is it?
So yeah, I'll show you, right? It's not bad, actually, from a practical perspective, but you do pay, all right? But the key thing is, so when you look at this, you say, oh, that's you know, it's a mixed integer program, that's bad. It's fractional, that's bad, right? But it turns out that you can relax this, right? So the relaxation gives you a fractional linear program, right? And it's still optimal. It's got the right total unimodular properties. And once I've got a fractional linear program, I can apply this, something I discovered a few years ago, Charnes-Cooper transformation for turning hyperbolic or fractional programs into LPs. And you get this really nice LP, right? So you can actually now solve this thing during training very fast. At serving time, maybe not quite fast enough, right? So what you might want to do is do exactly what you said. Maybe you want simpler computational strategies. Okay, so one thing you could do is you don't necessarily want to sort by the Q-bar values, but the Q-bar values times the attractiveness of the item to the user, right? So it's kind of like an expected value calculation. And just sort your n items and choose the top k. You might actually want to be greedy because every time I put a next item on the slate, it changes the calculus of the probability. So I could just have a greedy algorithm that throws the next item on that maximizes this term. Neither of these have any quality guarantees. They actually have unbounded approximation ratios, right? So that's why we're a little wary, but you're absolutely right. In practice, it still works okay, all right? So just, oh, good, we're pretty much on time. So we did two sets of experiments. First, some synthetic experiments because we wanted to have full control to see whether or not this actually worked depending on the characteristics of the environment. And then we did some live experiments on YouTube, okay? So in the synthetic environment, I won't get into the details at all. It's kind of we're actually, hopefully by the end of this month, releasing a configurable recommender system simulator where you can actually apply RL algorithms, configure users to have particular types of dynamics, and play around with RL algorithms, play around with new recommendation algorithms, because we think the RL community needs something more than Majoko, StarCraft, Atari, et cetera, okay? But very roughly, we've got documents that we're recommending. So those are just, there's a distribution over documents. They're characterized by some topic vector. Users have interests they're a point in this space as well. So it's kind of an interest vector over topics. And users also have some inherent satisfaction, right? Are they happy or not so happy with the recommender? And the items the items or the documents don't just have topics, but they also have a quality score, right? Some videos are good, some are kind of crappy, all right? In terms of user interaction, when I put a slate in front of a user, they're more likely to consume items on the slate that they're interested in, okay? And the thing that makes it an interesting RL problem is the user state dynamics. So when a user consumes an item, their interest stochastically, and can go in either direction, but it's nudged a little bit, at least stochastically, towards the thing that they just consumed, okay? Their satisfaction also changes. It increases or decreases stochastically with item quality. Higher quality items, they're more satisfied. Lower quality items, they become less satisfied, all right? And if they're less satisfied, they're more likely to terminate their session more quickly, right? It's implemented by saying the user has a time budget, which goes down more rapidly the less satisfied they are, okay? And this is interesting because we've got a distribution over documents such that the quality scores of these documents are correlated with the topics. Okay, so there's this interesting trade-off. To increase satisfaction, to keep a user more engaged for a longer period of time, you'd like to nudge their interest towards higher quality topics. But if they're not already interested in them, they're less likely to consume them. Okay? So it's a true planning-based trade-off. Okay? So just really quickly, I won't go through what all of these different algorithms are, but as you can imagine, I can do Q-learning, I can do kind of one-step SARSA, and realize we've got 3 different algorithms for computing optimal slates. We can do top K, we can do greedy, or we can do the full LP-based optimization. And if we're doing Q-learning, we can mix those up. We can use the full LP optimization at training time and use top K at serving time, for example, or vice versa. Okay? Yeah.
So why not using the policy gradient methods and instead of going through the combinatorial action, treat it as like continuous and go with the policy gradient method?
It's hard for like in a YouTube. It's really hard to parameterize. It's hard to parameterize a policy. A policy basically has to say, out of all of these videos, right, choose this particular slate in this state. Okay. It's also very hard to train. I mean, and I know we can do off policy gradient, right? But we really have to train purely offline. We don't actually want to do much training online.
How about testing?
What's that?
A/B testing. You do A/B testing.
Oh, we definitely do A/B testing, but we want to do as much learning with the massive amounts of offline data that we already have, without relying on A/B testing to do policy improvement. Right? We'll do A/B testing to validate and verify.
So you're saying coming up with the parametric form of the policy is difficult?
Yeah, right. And in particular, because in real life, I mentioned this stochastic action set, right? We have these stochastic action sets, right? So there's no fixed set of actions that we can put a distribution over, right? It's a different set each time, right? Even in the same state. Yeah.
I have a very simple question. The null slot, is it equivalent to somebody going through the entire slate, not clicking on any action?
That's right.
Or is it closing the app, or maybe...
No, it's not clicking on, conceptually think of it, oh, they just hit a refresh, right? There's a lot more, there's actually a more complicated story, because YouTube recommendations, it's not just the home page. Like, you go to the home page, then their watch next recommendation, they can search. I won't go into the long, complicated story of what actually was involved. Maybe offline. Yeah. Okay, thank you. Okay. So the point is, I just want to draw your attention to, say, Q-learning with optimal training, optimal serving, compared to a non-RL-based solution where we just myopically optimize user engagement, right? And we see some differences, the statistically different significances in performance. It doesn't look that great, but the thing is, it's very easy in the synthetic model to keep users engaged. So what we do is we actually compare their performance relative to a random baseline, right? And what we see is that the lift you can get from being optimal sequentially is about more than twice as much as the lift that you can get by being myopic, right? So we think there's a lot of value in actually optimizing over the long term when interacting with users. Okay. The second thing that we did was look at robustness to the user choice model. So if you didn't notice, the training procedure itself has a user choice model baked into it, right? That optimization procedure. And maybe you got it wrong. Maybe it's not a conditional logic model, right? Maybe it's a cascade model. Maybe it's something else. Now you can put a different optimization method within the training procedure. That's perfectly fine. But you may always have it wrong. So we actually wanted to test whether or not this strategy is robust to errors in the user choice model, right? So we actually trained the model using the multinomial logic or the conditional logic model, but we actually had users, and our simulated users, use a simple exponential cascade model to make their choices from the slate. So it's a very different slate. So we lose some value, but we still maintain the improvement over the myopic. Okay, so we think this process is fairly robust. And finally, just to test how successful this would be compared to full-blown Q-learning. In principle, if we just took every slate and treated it as an atomic item, Q-learning should learn the optimal policy, right? But like I said, exploration, generalization, data efficiency are going to be problematic. So that's why we use a very small test case here, because we actually wanted to do full-blown Q-learning where we enumerated all of the distinct slates. And what we see, again, is that here we're not even doing full Q-learning with the decomposition. We're just doing kind of one-step SARSA, and it still does a better job than full-blown Q-learning. Yep.
I'm just curious, sort of committing to one particular user model and then imagining that users obey something else is kind of maybe still less damaging than having the more real situation where you have a mix of users that exhibit all kind of behaviors. And what I'm kind of more curious about is, again, when my function fitting has to make all these trade-offs about like which users to, so will, like if I didn't conform to the user model, will I be the one who gets like crappy recommendations as a result compared to, like will my preferences get even more suppressed?
That's right. So one way to interpret this, I mean, it's a great question. What we're really interested in, going back to the very first part of the talk, we actually want to adapt our interaction strategy to the personal idiosyncratic characteristics of individual users. So if the way you respond, so how do these choice models work? It's something about your kind of immediate preference. And if I can do a good job, not just of understanding your immediate preference, but also basically your behavioral characteristics. We can actually fit this model to your, we're nowhere near that, but that's the ultimate vision. But even if you get it wrong, the thing that the thing that I'd note is we're still doing a better job. We're getting it wrong for everybody. We're still doing a better job than the current state of the art, which is purely myopic.
Right, but I'm sort of curious if you, for instance, in that experiment, say, just for some of the users switch to
Right, yeah.
then would those users still be better off compared to that base?
It's a good question. My guess is yes, but I don't say that with confidence because we're building here these are very synthetic experiments. In general, we're building a complex function approximator, and you're quite right. It could just skew things so that we're not serving particular users well. Yeah, it's a fair point.
Greg, can you maybe try to go closer?
Yep, this is the last slide. So just to quickly wrap up, so we did try this in a large-scale experiment with YouTube, using this to optimize slates on the YouTube homepage. I won't get into all the details of how you manage homepage versus watch next recommendations and so on. And here what we're showing, here we just did kind of SARSA one-step policy improvement, not full-blown Q-learning, and just use top K serving, okay, to your point, because it was very tractable. And what we're seeing here is for this particular user engagement metric that we're trying to optimize for over a longer horizon, kind of a session-style horizon, wasn't super long horizon. What we're seeing is the improvement in this engagement metric relative to the baseline myopic policy. Right? And what we're seeing is some pretty significant gain. So a 1% improvement in any metric in YouTube is actually pretty hard to come by. Okay. Let me skip over this. Here we're basically doing a lot of re-ranking. We actually weren't going through full collections of items. We're kind of focused on the things that YouTube would have recommended and just re-ranked them a little bit. And what we see is we're actually re-ranking things that are getting engaged with. We're doing the right thing. It's moving them to the top of the slate, and so on. Okay? So in the interest of time, I won't talk any more about Slate Q, but I do want to just maybe leave this one slide up and see if there are any kind of last-minute questions. We actually think there's a lot of really interesting questions that the RL community, we don't know how to solve them, that the RL community, I think, will be really well equipped to help tackle.
In the interest of time, let's take all questions offline, and then we'll be back in just about a little over, say, 12 minutes for the panel.